Here, we will be covering part 2 of isomers, and part 1 covered all our constitutional isomers as well as all our conformers. And we're gonna consider the fact that in configurational isomerism, we have a lot of things to kind of look at before giving the actual type of isomer. So it's kind of complicated and it deserves a separate discussion. So let's start. Remember that in order for us to determine isomers as configurational, we must first admit that, first of all, they have the same connectivity, meaning they have the same branching or position of functional groups or the actual functional group, which I have discussed in part 1. But also, on top of that, in order for you to confirm that they are config isomers, if you are asked the question, are the two isomers interchangeable? That is, can they be converted into one another by mere rotation or twisting of bonds? Then the answer is no. And therefore, it's like we're gonna try to find out why isn't it possible for one configuration isomer to be made into the other? The reasons differ. Usually, if it's because of restricted bonds, we call it a geometric isomerism. But if the reason for the non-interchangeability is asymmetry, it's optical. Now, all of those seem like magic words and like jargons, but that's the reason why we're gonna go after them one by one. First, if I have geometric isomers, the reason why the two isomers are not interchangeable is because of restricted movement. Usually, the reasons why we have restricted movement are double bond or a ring. Let me show you what I mean. Remember, and I will erase this, I just want to remind you of something. Remember when I told you like way before in hybridization that a double bond is 1 sigma and 1 pi. And when we draw it like that, isn't that like this? This is the sigma bond. And then the pi bond is going on top and below of the sigma. And now, the fact that the pi bond in the double bond kind of envelopes the entire bond on top and bottom means that if I'm gonna try to rotate one of my carbons holding the double bond, then the other carbon holding the double bond will automatically go along with it. So for example, if I may erase this, if I can imagine trying to put this CH3 at the bottom, since, somehow you can imagine that this bond is connected to this, that is rigidly connected here, that's connected here, you can imagine the moment you try to put your CH3 down, because of the restricted movement, you have no choice but to put the CH3 on the other carbon down also. Or if, for example, I try to put this carbon down, then this one will also go along with it, it will go up. That's the restricted movement we're talking about. Meaning, I cannot have a scenario wherein I have two methyls both up here. If I want to convert it to one on the top and one on the bottom, that's impossible because if I try to put this one at the bottom, this one goes upward and they're never on the same side. And here, if I put them both down, then they will always be on the same side. So that's what we mean by restricted movement. And I think for a lot of people, you already know how to name things like this. So what we do first is for this double bond, or the area of restricted movement, we try to cut it into two halves. And then let's pay attention to each carbon that holds the double bond. We have to make sure that for every carbon holding the double bond, we have one substituent, like this one for the left and this one for the right. Because if I do that, I can now confirm that in both halves, I have an H. One here for this left side, one for this right side. Although you can use the two CH3s for comparing, but I prefer using the H's. So if my H's are both at the bottom, or they are both at the top, then we will use the descriptor or the word cis, which literally means same. So my H's here are same here at the bottom, meaning both of them are at the bottom. Or if I try to put my two H's up, both of them would be on the same side, which is on top. This one is called trans instead because they never meet. They are opposite. And if I try to put this one at the bottom, the other one will just go along with it, going at the top. So it's either they are connected here or they are related in terms of this distance, or the other way around. So that's the meaning of cis or trans. And I do hope that this is already familiar to most of you at this stage. But again, remember it's not just a double bond that can have restricted motions. It can also be a ring, just like this one. The fact that I have a ring and my two OHs are here. Can you imagine this OH at the top going at the bottom? You're gonna have to flip the entire ring to do that. And if you're gonna do that, then that means if I try to put this down, guess what? This one will also go on top, which is exactly the same scenario that we had a while ago for double bonds. And therefore, we can also assign this one trans. For this one, both H's are on top, then this is cis. So that's geometric isomerism, okay? But don't think that every time you have a double bond, it automatically gives rise to isomers. For example, I have an example here, and then let's try to name it if it's cis or trans. I tried to cut it. And then what I told you a while ago is that each of these carbons holding the double bond must have one substituent. One, okay? One. This carbon at the right has none. It has zero substituents. Both of them are H, and those are not counted as substituents, right? Whereas on the other carbon, it has two. And not only does it have two substituents, those two substituents are exactly the same. Okay? And normally what we do is we try to find something at the left side and at the right side, and then we compare that, right? How can you do that here when the things at the left side are not even similar to the things at the right? What I'm trying to say here is that if this is the scenario, there is no cis or trans isomerism. Okay? So the requirement is I must have two carbons with only one substituent. If there's two or there's none, then it's impossible to give a cis or trans answer. This is another example. Normally, what we try to do is that for each of these two carbons, I'm going to try find something that's common in both and then compare them. Normally, our choice is hydrogen, right? So that means if I'm going to assign this the cis or trans, I should find hydrogen on the other side. No hydrogen here, no hydrogen here. So, like, you cannot use also cis or trans simply because there's nothing to compare. How about OH? Like, also, there's no OH on the other side, so there's really literally nothing you can compare. And this is a question mark because later on I will teach you how to give its proper description. It's actually in terms of letters. But before we do that, I want to orient you on something called the Cahn-Ingold-Prelog Rules, sometimes abbreviated as CIP. So these are prioritization rules. And it doesn't make a lot of sense if you study it as a standalone topic, but it will make sense when you apply it later. Now, I just realized I forgot to put examples for the practice at the right. So let me pause for a while as I try to draw something there. Okay, so I put something here for us to answer later. Let me first run you down through the rules first. If you're going to assign the top priority, you should assign it in order of highest to lowest atomic number. In fact, I already made it here convenient such that you see the order of the atomic numbers among some of the most commonly used elements. Of course, iodine is the heaviest. In terms of atomic number, it's the highest, so it's top one, followed by bromine and so forth. Okay. In case of a tie, for example, I'm comparing two things that the first atom is carbon. Proceed to the adjacent bonds and find the highest atomic number among them. It's like you're going for a tiebreaker of some sorts. And take note that if I have a carbon double bond C, even though that carbon is only a single carbon, we count that as two carbons simply because of the double bond. Or for example, if I have this carbon and this is triple bonded to the other carbon, even though this is just a single carbon, the fact that we have a triple bond to it means that we're gonna count that thrice the carbon. And still, probably it doesn't make a lot of sense for some. So let's go straight ahead and practice it. First, I have here set A. I have here 3 substituents. And we are being asked, give the number 1 rank, the highest rank, then by the next, and then the next one. Take note that this is the bond that we first consider. Okay, so here my bond is connected to O, here my bond is connected to C, and here my bond is connected to N. This is an easy example because all my first atoms are different. We know that oxygen is the highest in terms of atomic number, followed by nitrogen, followed by carbon. So this is top 1, this is second priority, this is last priority. Now how about set B? In all cases, you have carbons, right? And the only difference is the type of alkane. So for example, here I have the type of hydrocarbon, I mean. Here I have an alkene, here I have an alkane, here I have an alkane, but it's drawn differently. And here we need this one. In case of a tie, proceed to the adjacent bonds and find the highest atomic number. Meaning, after you're done with this, for example, let's try to cancel this out. Alright, we cannot make a decision on the carbon, so let's look at everything else after the carbon. Remember that the carbon here that I kind of erased is attached to one H and double bonded to one carbon, so that's counted as 2 carbons. Whereas the carbon here is attached to 2 hydrogens, so 2 hydrogens, and then attached to this single carbon. Whereas this carbon here that I erased is literally attached to 3 different carbons, C, C, C. And of course, the one which wins has the highest number of atoms with the highest atomic number. Of course, between H and C, C has the higher atomic number. It's like saying the rank 1 here is the one with the most carbons attached. Now this one has 3. So this is the clear winner, followed by this one which has 2. And then this one is the least priority because it's only 1 carbon. Okay. Then finally, how about this one? So notice our first atoms are carbon, oxygen, and carbon. And the moment that oxygen is there, it already wins, so this is the top 1 priority. Now how about this? Between a triple bond carbon and a COOH, who would win? Well, if this is the tie, what's our tiebreaker? The fact that my C triple bond C is equivalent to 3 C's, and my COOH is equivalent to 3 O's, right? Because one of the O's there are double bonded, so that's the 2 O's. One of them is single bonded. It's not even a match. The fact that I have 3 oxygens versus 3 carbons is downright easy to answer, that this is higher priority compared to this. And now, if you haven't caught that, you can replay this several times because we're going to apply the Cahn-Ingold-Prelog rules for naming alkenes and the other type of isomers. Alright, so let's try doing that. So here, note that I already gave the clue. Instead of using the word trans, the moment that you use CIP rules, you're going to use the letter E. For you following CIP rules, but you get something that's kind of cis, you use the letter Z. So how do we apply the Cahn-Ingold-Prelog rules to our double bonds? Remember a while ago when I gave you this example that what if I have a carbon here, which has 1 substituent, but is double bonded to a carbon with 2? That's a problem because normally what I do is I compare the 2 hydrogens, but I can't do that here because I only have 1 hydrogen at the left. At the right, there's none. So we cannot use the classic cis-trans configuration. So what we're going to do is in every half, we're going to determine which is the priority. It's always a battle between up and down. So it's carbon versus H. Of course, the clear winner in priority is the carbon on top. But for the right side, it's CH3 versus CH2, CH3. Remember, right now, you're having a tie here following the Cahn-Ingold-Prelog rules. So next, we know from CH3, its next attachments are H, H, and H, these 3 hydrogens. But here I have 2 hydrogens and 1 carbon. And of course, we know that anything with carbon is higher ranking than anything without. So with erasing what I did here first, it is very clear that the one at the bottom is of higher priority. Now, what can you say? Our two priority groups are kind of on the opposite side, right? So you might answer trans. But do not use trans here. Since you followed the prioritization rules, instead of writing trans, you write here the letter E. So we call this one the E isomer of whatever compound this is. Next, if we have something like this, same rules. So here for this carbon, it's a battle between O and C. We know that oxygen is the clear winner there. And here on the other side, it's a battle between H and Cl. It's also no contest, the winner is Cl. And just like a while ago, my priority groups are on the opposite side, so this is also an E isomer. Finally, we have another example here. So between this one and this one, it's a tie. And I think it's already simple to see. This one has single bond at the top. Here, double bond. And most likely, the double bond will trump over the one with the single bond. So this is the priority. Whereas here, it's between carbon and oxygen here. Don't be fooled by these two oxygens. You don't look at them. You look at the carbon first and foremost, right? So between carbon, which is directly attached to this carbon, and this oxygen, which is directly attached to this carbon, C versus O, the clear winner is oxygen. So meaning, I have here my two priority groups, both at the bottom, both on the same side. But since you use the Cahn-Ingold-Prelog rules, you're not going to use the word cis, but instead the letter Z. So I hope that this clarifies the difference of the usage of cis, trans, and easy. You know, in dumb terms, like in the laziest possible if explaining it, if you cannot assign cis or trans because even regardless of how you try, you don't come up with anything, most likely you're going to use E or Z, okay? But you won't really realize that until you keep practicing. I'm sure over the internet there are a lot of practice questions for E and Z configurations. But that's it for geometric isomers. The last thing we're going to discuss about isomers are what we call optical isomers. And first of all, before I proceed, optical isomers are called as such because they have a property called optical activity. I don't want to discuss this completely, but I will do a little bit of it. So here I actually had a dedicated slide for this. So optical activity, first and foremost, is measured using an instrument called a polarimeter, simply because what the polarimeter does is it makes polarized light, which is light that comes in only single direction. Okay? Yeah. And let's say I try to compare an optically inactive sample versus an optically active sample. So what will happen to this polarized light that moves in only one direction? If my polarized light or one direction only type of light goes through an inactive sample, meaning nothing happens, it will stay the same. Like the angle is exactly the same as the original. So it's the same. There's no change. But if I go through an optically active sample, what will happen is sometimes your direction is rotated clockwise, sometimes it's rotated counterclockwise. For terminology's sake, if the spin is clockwise, it's usually called dextro-rotatory. If it's counterclockwise, then we have a levo-rotatory rotation. And that leads me back to my slide a while ago. How do I know that my compound is optically active? How do I know that my compound is an optical isomer of something? That is if you have something called a chiral carbon, which can also be called an asymmetric carbon or a stereogenic center. There are two main requirements for you to have in a chiral carbon. That is 4 different substituents. Okay, I need to satisfy them. It must be 4 and different. If I have 4 substituents, but there are some things there that are not the same, no chirality. Or if I have all substituents different, but I only have 3 substituents, it also cannot be chiral. So for example, this carbon is a perfect representation of that. I have a carbon that is bonded to 4 different things. And if you look at those 4 different things, CH3, Cl, H, and OH, all of them are different. This carbon is is an example of a chiral carbon. And usually to indicate that I have a chiral carbon here, then we add an asterisk, like so. So now, do you know that here in assigning our optical isomers, the letters that we use are R and S. And R and S will depend on a certain technique that I will teach to you right now. So listen up. First, using the same CIP rules, Cahn-Ingold-Prelog rules, as in atomic number based rules. You have 4 substituents, right? Determine them, which is rank 1, rank 2, rank 3, and rank 4, using atomic number. Clearly, if you remember this, chlorine has the highest rank, has the highest atomic number, so that's 1. Then O from OH is 2. The carbon from CH3 is 3. And the H is definitely 4. Now, that's the first step. Normally, the second step is that you put number 4 at the back. Notice I already put it at the back for our convenience, such that the only thing we need to do now is to make a spin from 1 to 2 to 3. From 1 to 2 to 3 and back. And what type of spin is this? I'm going here in this direction. Is it clockwise or counterclockwise? Well, obviously, it's counterclockwise. And if it's counterclockwise, I assign the letter S. So I can call this thing my S isomer of this compound. But in this case, look at this. This is, as usual, my 3. This is my 1. This is my 2. This is my 4. Normally, I should put number 4 at the back. But here it's already at the back, so we don't need to focus on this anymore. And now my spin is 1 to 2 to 3 and back is, guess what? It is clockwise. And if it is clockwise, we assign this, or we call this the R isomer of whatever you call this compound. Okay? So that is how you actually identify the R or S letters. Alright? And usually, we call these things as enantiomers because the fact that the R isomer and the S isomer, they look very much alike. In fact, let me try to erase this and then let me ask you. Did you honestly think at the start of the video, of course, if you have no idea about this before, do you honestly think that these two are different compounds? For sure, some people would have noticed these two structures and said, aren't they the same? But no, they're not, because when we already tried using the Cahn-Ingold-Prelog rules, we determined one was S and one was R. And they are similar but not exactly the same. Like, I don't know, like our two hands once again. I mentioned this in part 1. No? So, the fact that these two are mirror images of each other, we have a special name for that, and we call them as enantiomers, which are mirror images. Okay? And the property of them, what's unique about them is that an S isomer can never become an R can never become an S. And I think that is very much fitting in our definition of configurational. Config in the first place. Config in the first place means not interchangeable, right? So that means I cannot interchange my S to an R or R to an S. Unless I break a bond, but that's outside our working definition. Okay? And another term that we can use for enantiomers or an adjective is the word non-superimposable. Meaning, just like your hands, you cannot place one hand on top of another, both of them face down, and expect that both of your thumbs will match, both of your pinkies will match. Man, if that happens, your hands are weird. That's not normal. Okay? So we can use the word non-superimposable. And the word racemic mixture or racemate refers to a mixture of enantiomers. So if ever I have a test tube, I have molecules of this, and I have molecules of this, I can call my test tube, I can call the reagent in my test tube a racemic mixture. Now, enough of that. Let's have another example of determining whether it's R or S. So just like a while ago, the fact that the carbon here at the middle has, even if you check it, 4 different substituents, it's chiral. Now let's rank. Bromine is definitely the largest, so this is 1. Followed by COOH. Followed by methyl. And we know that hydrogen is always 4. Remember what I told you a while ago that if you have your 4 there, you must place it at the back. And this is a problem because sometimes if your number 4 is not at the back, you have to use your 3D imagination, trying to spin around the atoms, finding a way to put number 4 at the back. And I really can say that it's not easy to do. But here, okay, you can try repeating watching this several times until you get it. Imagine that what I can see here is I can imagine I'm holding this CH3 group. Let's say my hands are on that CH3 group. And I'm trying to twist my angle here or my bond here in this direction. Such that what happens is, if you can think of it, what happens is this hydrogen at the front will move at the, oh sorry, wait, I'm trying to imagine it also. It's difficult. Even for me, it's not really that easily imaginable. So let's see. So if I try to spin it, yeah, if I try to spin it counterclockwise, what will happen is that this COOH will go to the front, okay? This hydrogen will go at the back, and then this bromine will spin all the way to the top. Following what I said, it will now look something like this. So I can see my my bromine going at the top. Then my COOH will be going down. And then my H will be going at the back. And really, the best way to do it is by practicing and trying to be familiar with your spatial orientation. So I cannot even say that mine is perfect or like very good because right now I'm trying to analyze if what I did was correct. But it looks like what I did was correct. Okay? So now this is going to be our structure to evaluate. So once again, this is 1, this is 4. Now it's at the back, so we can now uh, do the spin. This is 2, this is 3. And my spin from 1 to 2 to 3 is, well, counterclockwise. And because it's counterclockwise, we assign the letter S. Okay? So that's how you do it. And yeah, the fact that I too am having difficulties myself recording this means that it's not something that's easily done. You really have to imagine something 3D on your mind, and that to me is crazy. So it's acceptable if you need a lot of time to practice on things like this. But we must proceed, no? We must realize that for some compounds, they have more than one chiral carbon. What you only see right now are compounds with just one chiral carbons. But there's no rule saying that you can only have one. In fact, for example, in this case, I have two. So, for example, I kind of realized that, hey, just an example, just to get the point across. Hey, I noticed that this carbon at top has an R configuration, and the one at the bottom has an S configuration. So, what do I have now? Okay. What you have now, if you have two chiral carbons, is the possibility of having four possible combinations. What if my first carbon is R, my second chiral carbon is S? Or what if my first carbon is S, my second carbon is also S? Or what if both of them are R? Or what if one was S, the first one was S, the second was R? There's a lot of things going on, right? And now I must introduce another term. You already know about the word enantiomer. When you say enantiomer, let me repeat, it means mirror image. But you know what? To say that something is a mirror image means that all of my chiral carbons have been interchanged. Or the proper word that we sometimes use is inverted. Meaning R becomes S or S becomes R. For example, what is the enantiomer of RS? Then, in order to give me the enantiomer of RS, all, meaning both of my letters should be reverted. So that means the enantiomer of this is wherein the first letter should now be S and the second letter should now be R, which is what you see here, right? So that means that this one and this one are exact opposites. They are mirror images. So I can say that these two are what we call enantiomers. Enan. Okay? Or how about this? What is the enantiomer of RR? Well, it means I need to invert both, right? So the opposite of RR is, well, SS. So that means that between RR and SS, they are perfect mirror images. You can also call them as enantiomers. But now the problem arises with this. How about this? What if I see here, let me use a darker, let me use red. Let's say I have my my R carbon becoming S. So yeah, it's inverted. We normally see this. But what if my second letter S stays S? So can you say that both my letters have inverted when it's clear here that one of the letters did not change? So we know it's not the case, right? So there are some cases that we have isomers that some, only some, but of course some means not all. Chiral carbons are inverted. And in this case, the term that you use for these two isomers are diastereomers. So I can say that an RS isomer of something and an SS isomer of something are called diastereomers. Or for example, RS and RR, my first letter did not change, right? My second letter changed from S to R. So only some, not all changed. So this is a diastereomer. From RR to SR, it is clear that the first letter changed, but the second letter R stayed R. So that's also some. And I think you get the point. That the fact that if I was not able to invert everything, you cannot call that an enantiomer. But the fact that something changed, you can call it something else, and that is diastereomer. So keywords are all and some. And I think that's not too difficult to understand. Lastly, we have compounds which are called meso compounds, and they are compounds with two chiral carbons with plane of symmetry. The most common example the textbooks uses this molecule. They call this thing tartaric acid. In fact, in textbooks, they really show you the 4 different isomers of tartaric acid. I'll just use the meso one. So why is this the meso tartaric acid? That is because if you try to analyze the configurations of these, you will come up with the conclusion that one of them is an R carbon or an R configuration, the other is S. And then if you try to split it here at the middle, look at what we have. The upper part has an OH, a COOH, and an H. The lower part also contains an OH, an H, and the COOH. Isn't that symmetrical? That's weird, right? Because all this time, I taught you that chiral carbon is a sign of asymmetry. But it's possible for you to have points of asymmetry or non-symmetry, but as an entire compound, it's symmetrical. Quite ironic, isn't it? And what now if there is symmetry? Isn't it that I told you a while ago that usually optical isomers have asymmetry? And therefore, asymmetry usually means optical activity. So again, asymmetry or lack of symmetry is equal to optical activity. How about this? Isn't it that this one has symmetry despite the fact that it has chiral carbons? What I'm trying to say here is that mesocompounds are unique because they are the only compounds with chiral carbons that are optically inactive. Makes sense, right? If there is asymmetry, there's activity, but if there is symmetry, it's inactive. So they're kind of what they call chiral achiral compounds. Chiral because they do contain chiral carbons, but achiral because at the end of the day, there's symmetry, and unlike most chiral compounds, they do not rotate plane polarized light. And that is the unique thing about meso compounds. And again, just like what I taught before or what I mentioned in my closing statement for IMFs and structural effects, isomers take a long time to discuss. Normally, I discuss this in 3 meetings, which is like almost 5 hours. And for me to discuss this in like 2 20-minute discussions, okay, that's very short. So notice we don't have a lot of practice items. And if you actually want, you may request, and I will record it as a separate video. But here is the end of the discussion on types of isomers. Hope you got something from this.